we've defined what a mineral is. So now let's go about how we identify those minerals. You'll see some common tools that you'll be using, including a fingernail, a penny, an iron nail, a piece of glass, and over here on the left are what we call streak plates, and these are made of porcelain. So let's look at some of the physical properties. These are a result of a mineral's chemical composition, or again, what it's made of. So let's start with the very basic, easiest thing to identify as far as a physical property, and that's color. It's the most obvious, right? You can just pick up a mineral sample and see it, but it's also, unfortunately, the least reliable. So you'll notice up here, I have a picture of fluorite. These are all samples of fluorite, yet they're different colors. And so there's small amounts of impurities in them that change the color quite a bit. So that's one problem with color is I can have the same element or the same mineral and it can be different colors. Here's the next problem. What if I have two minerals such as these that are colorless? These two look very similar, translucent or clear, but over here I have calcite, and then over here I have halite. Very, very different. So again, color, while most obvious and easy, is unfortunately also the least reliable. What is a little bit more reliable is something called streak. And notice I mentioned that porcelain plate in the first slide. That's what this is. It's called a streak plate. And basically what it does is it's harder than most minerals. And so if you scratch the mineral on the streak plate, it will leave a streak or the color of the mineral in its powdered form behind. And so notice the sample that this person is holding looks kind of black in color, yet look at the streak that it leaves. It's this reddish brown. This is hematite. So no matter what color the hematite is, the streak will always be this red-brown rust color. There's also what we call luster. It's basically how the light reflects off of the surface. And there are two basic kinds, and those are metallic and non-metallic. Obviously, looking at these two samples, this one looks like a metal, and this would be the metallic luster. And this one, of course, does not look like metal and would be non-metallic. We then also have cleavage, and that's basically the tendency of a mineral to break along an even or flat surface. So you notice that this, and this is mica, is very flat and even. Same with this, has nice flat surfaces. Those have pretty good cleavage. And so if something doesn't cleave, it fractures. And so fracture would be breaking unevenly. And so this is a piece of obsidian, which is an igneous rock. And you'll notice kind of these curvy lines in it. That is called conchoidal fracture. It's a type of fracture. So fracture is typically very uneven or irregular. So let's talk for a moment about hardness. You'll see I have a scale here ranging from 1 being the softest to 10 being the hardest. I think most of us can come up with, if I asked you what's one of the hardest materials you can think of, most of us can come up with diamond. What most of us may not be as familiar with is on the soft end of the spectrum here is talc. And you use it all the time and may not have known it. So if you've ever used talcum powder or baby powder, that's ground up talc. It's so soft that you can actually scratch it with your fingernail. So what you see here are some things that you would use out in the field if you had, if you were out somewhere and collecting samples, you could use. You would have, your fingernail available to you, a copper penny, a nail, a piece of glass, a streak plate, are all very easy, portable things to take with you. So this scale is called Mohs hardness scale, named after the person who developed it, the scientist who put this together. And so you'll see 1 through 10. And so we compare minerals hardness to these known hardnesses. Then we have crystal shape. There are 6 basic crystal shapes that you'll see listed here in this photograph. And so sometimes the crystal shape is displayed internally, meaning you can only see it under a microscope, but some of the minerals actually display them externally. So we had a piece of quartz in our other slide, and I told you had 6 sides. So it was a hexagonal crystal external shape, right? And then there's things like galena. You'll see that in class, and it always looks very square-like, and it's an example of a cubic crystal shape. But these are the 6 basic crystal shapes. Density is also very useful, and here I have the equation for you. Density equals mass divided by volume, and so that's very easy to find. I can take the mass of something by putting it on a scale, and I can easily determine the volume of a sample by using water displacement methods, and you'll do both of these in a lab. Some of the minerals have what we consider special properties. And so this is a pretty excellent picture. Fluorescence and phosphorescence are very similar. Exposing them to black light, they will actually glow some of these crazy colors. And they should remind you of some fluorescent colors or neon colors that you've seen before. So some minerals have this property naturally. So again, exposed to a black light, they will do what we call fluoresce. Chatoyancy and asterism. So the chatoyancy is the sample of tiger eye down here, and the asterism is this sample where you can kind of see the starburst coming out of the middle. These are special properties also that you can see in these particular minerals. Double refraction. So one of the samples that I showed you at the beginning that was colorless and looked like another sample was calcite. And so one of the key ways I can figure out which one is calcite is by setting it on some type print. And you'll see the word calcite, for example, here is doubled. That's a natural property called double refraction that we see present in samples of calcite. Some samples are naturally magnetic, and magnetite is a good example of that, conveniently named or appropriately named. And so some of them are magnetic naturally. And then lastly, some of them are radioactive. So if I used a tool called a Geiger counter and I held it up to some of these radioactive samples, the counter would make a bunch of noise. It would take off, indicating that it had a high degree of radioactivity. So that results when the unstable nuclei present in the mineral begin to decay. So again, this can also help us identify some particular minerals.